Okay, now we're doing section 4.5. Now in section 4.4, or 4.2, we're talking about the relative max and the local max and the local min. And now we're going to talk about the absolute max and min. And absolute means the point that's absolutely the highest in the whole interval and or in the whole graph, whatever. And the min is the point that's absolutely the lowest. Now, it might be a local max, it might be a local min, or it could be, first of all, if there's three local maxes, then the top, not all of them are the absolute max, only the top one could be the absolute max. Plus, you just have to check the endpoints. So really, it's pretty simple. You just got to look at all, if you want to find the absolute max, you got to find all the local maxes plus the two endpoints and pow, whichever number is the highest, that's your max. That's your absolute max. So here's the definition. If f of c is greater than or equal to f of x for all x in the domain of c, then f of c is called the absolute maximum of f, which makes sense, meaning that there's nothing else that's bigger than f of c. Now, if f of c is less than or equal to f of x for all x in the domain, then f of c is called the absolute minimum. Now, an absolute max or an absolute min is called an absolute extremum. And again, that's just a word. Who cares? It's just a word. Let's move on. So here, if I want to look at the absolute max, well, this doesn't have an absolute max because that's a local max. Down there is a local min, but here it goes up forever. So, there's no actual max. And here it goes down forever. There's no actual min because you can't say 1 million is the max because it's going to get to 2 million. It's going to get to 5 million. It's going to get to 1 billion, 1 trillion. It'll equal the number of hamburgers sold by McDonald's eventually, whatever the number that is. So on and so forth. Now, this sucker does have an absolute max because this local max is also the absolute max. You can just see it from the graph. And this point right there is the absolute min. Now, this graph has a min, but there's no absolute max because it goes up forever. And this has a max, but there's no absolute min because it goes down forever. So that's so there's a lot you can just get looking at the graph. Now, there's something called the extreme value theorem. Who doesn't want extreme value? Let me get my picture out of the way. It's blocking traffic. Okay. I mentioned this before, and I'm just going to say it again. When my picture is here, sometimes it gets in the way of what I'm, the thing we're looking at. The reason, and it would be easier for me if I just didn't have the picture. I could just click the thing where I stopped I stopped video feed. The reason I do it is I just always want to remind you that I am a human being. I am with your class. I'm here. You can call me on my phone. You can call me. You can email me. I am an actual living person who's here right now this semester in fall of 2021. So that's why I keep my picture, my movement video picture up. So you see, it's me, a human being talking, not just some machine voice. Although who knows, maybe I am a machine. Did you ever have to? I find ironic when sometimes when you have to prove to a computer that you're not a robot. You ever have that? Anyway, so if a function is continuous on a closed interval, now closed interval is very important, as we're going to see, then it will have both an absolute max and an absolute min on that interval. And again, the absolute max is either going to be one of the local maxes or it's going to be one of the endpoints. The absolute min is either going to be one of the local mins or one of the endpoints. So here, that's the absolute min. This guy up there is the absolute max. Yeah, I have these local ones, but the local ones are not as high or as low as the endpoints. Here, the local one is higher than the endpoint, and here, because the endpoint is over there, and here the local min is higher than that. And notice that this graph is the same graph. It's just here I'm looking at the interval from 2 to 12, and here I'm looking at the interval from 4 to 10. So as you can see, the domain, the interval, will make a difference of what's the local max and what's the absolute max, what's the absolute min. Now here, I have this guy up there on top is the absolute max, it's the highest thing. And this endpoint over here is the absolute min. Again, that's because I'm going from 4 to 8. So it really depends. The answer, when it comes to the absolute, it really depends on what interval you're looking at, where the interval is that you're looking at. Because am I looking at the whole graph or looking at this little part, a small part there? Here, I have, it looks like we have a tie because that's because this point and that point, they seem to be tied for absolute max, because they both equal 105. And here, these points here are also tied because they both equal 73. Oh, by the way, what is the function? So the function, I forgot to say, sorry, oops, I forgot to mention. The function is x to the third minus 21x squared plus 135x minus 170. So we're looking at only pieces of the graph. Depending on which piece of the graph I looked at, that'll tell me which is the absolute max, which is the absolute min. And, you know, it's pretty much, think of it as just common sense. Don't think of it as something so mathy. Just think of it just in more in common sense terms. Okay, let's move on. So to find the locating the absolute extrema, well, absolute extrema, that's mins and maxes, if they exist, must occur either at the critical numbers or at the endpoints, which is what I said. It's either local maxes, local mins, or endpoints. And it's pretty, you know, that's pretty much common sense. So let's do an example here. Let's look at f of x equals x to the third plus 3x squared minus 9x minus 7. And we want to look at it over 3 different intervals, from -6 to 4, -4 to 2, and -2 to 2. Now, by the way, you always have to make sure that the function is defined in the intervals that they give you. Now, this particular function is defined everywhere, so no intervals can be a problem. But for example, if this function had like a square root in it, I couldn't go from -2 to, you see what I'm saying? Anyway, we know it's continuous. Polynomials are always continuous, and differentiable and all those kind of cool things, and defined and everything. So we take the derivative. F prime is 3x squared plus 6x minus 9, which then I can factor x minus 1, x plus 3, which means +1 and -3 would be the critical numbers. And we see that we look at the -6, -3, +1, and 4. Now, I understand the -3 and the +1. That's, we just said, those are the critical numbers. Where the -6 and the +4 come from? Came from this. That's the endpoints of the interval. So basically, I just check. All I literally have to do is take these 4 numbers and plug them into f, the original f, not f prime, but the original f, to see how high it is on the graph. So I plug these all in. You see that -61 is the lowest, +69 is the highest, and pow, there's my absolute max, my absolute min. And for the other ones, it's the same idea. I'm always gonna plug in -1, -3, and +1. But I also plug in the endpoints, -4 and 2, and you see that 20 and -12, those are my winners. 20 is the highest, -12 is the lowest. Now in the last one, in C, if you notice, -3, which is one of the local extrema, -3 is not part of my domain, because I'm only looking between -2 and 2. So I'm only going to plug in -2, +1, and +2. -3 is outside of the domain. So therefore, by default, the absolute max is going to be this first guy right here at -2, which gives me a value of 15. And my absolute min is going to be the number, this one here, the -12. So, like I say, the particular domain that you choose makes a difference. That's what I'm trying to say. The particular domain makes a difference. Alrighty. Now here you see, if you have an open interval. Now we said in the extreme value theorem, we said that the interval needs to be a closed interval. What's wrong with it being an open interval? Well, if it's an open interval, I could have a situation like this where it's asymptotic, and it's never actually a max, because it gets closer and closer to 1. It'd be 0.9. Then if I go out further, it'll be 0.99, then 0.999, 0.9. You know, it keeps on getting bigger, keeps on increasing, but I can't say there's one value that's the highest value, because if I just move to the right, I'll find a higher value. And here, if I move to the left, I'll find a lower value. Was there a song with that? To the left? Was it to the right? I forget the song. Anyway, here also it's asymptotic. I'm going down, down, down to that point, that missing point. But as I get closer and closer and closer, I may get closer and closer to I guess 3. But I get to 3.1, 3.01, 3.001, 3.00001. So I'm getting lower and lower and lower, but there's no one number which is the lowest, because 3.1 is not the lowest, because 3.01 is lower, and 3.01 is not the lowest, because 3.0 is, you know, and so forth. Here also there's no max because it just goes asymptotic that way. So it just keeps on getting bigger forever and stays within the open interval. See, in a closed interval, this would never happen. It would eventually have to hit, it would have to stop somewhere. But these are open intervals. That's why you won't necessarily have an absolute extrema in an open interval. Okay, well, I know you missed second derivative, so let's see how that plays in. So here's a nice theorem. And I think it's I think it's kind of like common sensey, that if C is a critical number such that f prime of C is equal to 0, so that'll be a good candidate for horizontal tangent. And if the second derivative is positive at C, then f of C is a local minimum, because if it's concave up, that means the bottom is down here. Similarly, if f double prime is negative, that means it's concave down, so you have a top up there, and blah 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 blah. And if there you go, that's it. So this is just telling us local max. This is for local extrema. It's a local max or local min. So but I need that the derivative has to be 0 no matter what, and the second derivative has to be either positive or negative. If the second derivative is 0, then the test is just inconclusive. It doesn't apply. If you get it, you're not going to get anything from it. So just forget about it. Okay. Find the local maximum and minimum for each function. Use a second derivative test for local extrema when it applies. So first, let's just do A. I don't think I'm going to do all of these. I'm just going to do A. 4x to the third plus 9x squared minus 12x plus 3. So f of x is equal to 4x third, 9x squared minus 12x plus 3. F prime is 12x squared plus 18x minus 12. And we're factoring f prime. That's important because when we factor it, we could see when it equals 0. So it equals 0 at x equals -2 and x equals positive 1/2. And then f double prime is 24x plus 18, which is, again, is 6 times 4x plus 3. So the critical numbers are going to be -2 and 1/2, or 0.5. So I have to see what's going on with the second derivative at that point. Well, if I plug -2 into the second derivative, I get -30, which is negative. So that's a local max because it's concave down, so I have a crown on top. And this guy, I get +30 for 1/2, which means it's concave up. So I have a local min at that point. So 0.5 is the bottom of the valley. -2 is the top of the hill. And that is, now if when we plug -2 into the original function f of x, we see that -2 gives us +31, and that's going to be, and so -2 comma 31 is going to be a local max, and 0.5 comma -0.25 is going to be local min. Okay, and let's just go quickly through all these. I said we'll only do A, but may as well. I'm going to roll here. By the way, if I ever don't, you can always text me, email me, whatever, that you'd like to see me work out a problem. Let's say there's a problem in the lecture and I skipped that problem. Usually I won't, but I might. Or let's say there's a problem on the homework and you just don't know how to do it. You could always get in touch with me. Now, if it's a homework problem, there's I'll show you. I think I might have shown you this. There's something called Ask My Instructor. When you click Ask My Instructor, then Math Excel itself sends me a direct email, and it sends me a link to the problem that you're talking about, so I have all the information in front of me. Anyways, so we have x times e to the -0.2x. Use product rule, and that gives us, and then factor everything out, and we get x to the -0.2x times 1 minus 0.2x. Again, we're gonna have to do some product rule and some chain rule, a couple of fun things here. Actually, we did chain rule the first time also. Finally, we get e to the -0.02x times 0.04x minus 0.4. So the critical numbers are going to be 1 divided by 0.2, because 1 divided by 0.2 is going to make this 0. And of course, 1 divided by 0.2 actually equals 5. So the critical number is 5. Now let's just take 5, plug it into the second derivative, and I get e to the negative 1 times the negative 0.2, which is negative. I don't care what it equals. I just care if it's positive or negative or 0. And it's not 0. It's actually negative. So that means you have a local max, and that's exactly what we want to know. Alrighty. Let's look at C. So f of x is 1/6 x to the 6th minus 4x to the 5th plus 25x to the 4th. When I take the derivative and factor everything out, I get x to the 3rd times x minus 10 squared. Now I take the next derivative. Now I can take the second derivative either by differentiating these guys here, which is probably easier, or I could use product rule over here, product rule and chain rule over here. But it's probably easier just to go straight this way. So if it's easier just to go straight this way, why did I bother factoring it? That was just because I want to see when the function equals 0, when the first derivative equals 0. Anyways, the critical numbers are going to be 0 and 10, because if x equals 0, my first derivative is 0, and if x equals 10, my first derivative is 0. So I take those numbers 0 and 10, plug them into the second derivative to see if it's concave up, concave down. But now for 0, I get 0 for the second derivative, which means the test fails. The test, just throw out the test. You get nothing from it. And f double prime of 10 also gives me 0. So again, the test fails. Now that doesn't mean we do or do not have a max or a min. It just means the test won't work. So I have to go back to my first derivative test. Remember, we had the first derivative test to see if the first derivative is changing signs. Well, when we make a table, we see that the first derivative, if you're going all the way up to 0, from negative infinity to 0, then from 0 to 10, then from 10 to infinity, we're splitting that up. We take our test points and we see the first derivative goes from negative to positive to positive. So this guy at 0, I'm going to have a min, but at 10, I'm not going to have a min. And that's exactly what we're saying. F of 0 equals 0 is a local min, and that's it. We do not have a max or a min when x equals 10. And that is that. Now, you're probably all wondering, what about the second derivative test for absolute extrema on an interval? So if f is continuous on an interval with only one critical number, c, and it's an open interval ab, that means if the derivative is 0, the first derivative is 0, and the second derivative is positive, then f of c is the absolute min. If the first derivative is 0 and the second derivative is negative, then f of c is the absolute max of f on the interval I. And that's, again, this specifically works for open intervals. Isn't that funny how some things work specifically for closed, some work specifically for open? That's why you have to. You got to know. That's why you got to know what you're doing. Okay. So let's find the absolute extrema on an open interval. So if I look at x plus 4 over x, if I take the derivative, I get 1 minus 4 over x squared, which if I put, I want to combine this into one fraction, because that's easier to see what the critical numbers are that way. And I get, I factor this, I get x equals positive 2, x equals negative 2. Those are going to be my two critical numbers. Now I take the derivative. For the derivative, I'm just going to go back to the simple form, and I get x over x to the 3rd. So I want to check out positive 2 and negative 2 and see what I get. But when I plug in positive 2, I'm going to get a positive number. When I plug in negative 2, I'm going to get a negative number. So f of 2 is the absolute minimum, and since the limit as f of x goes to infinity, then f has no maximum on. It's going to just go up forever, so there'll be no minimum. By the way, how come I have 2? What about negative 2? Isn't negative 2 good? Well, negative 2 is great. It'll give me a nice answer. However, it's not part of my domain. The domain here is from 0 to infinity, so the domain only has positive numbers in it. So even though negative 2 would have been a great number to test, I'm not testing it because it's not part of the domain that we were given. It's not part of the domain that we're working with. Now for this one, ln x squared minus 3 ln x, so I take the first derivative, and again, I'm going to have to use a chain rule here. So it's 2 ln x times 1 over x, and this is going to be 3 times 1 over x. That's not chain rule, that's just a straight derivative. I put it into one fraction, I get 2 ln x minus 3 over x. So the critical number is going to be x equals e to the 3 halves, because if x equals 3 to the halves, the top becomes 1 minus 1. And now I just take the second derivative, crunch, 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 and I get this. And how you take the second derivative is up to you. You can use product rule, chain rule, whichever way you want to do it. But now I want to take e to the 3 halves, plug it in, and see what I get. So when I take e to the and e to the 3 halves is positive, so it is inside my domain. If it was not inside my domain, there'd be nothing to talk about. Well, if I plug e to the 3 halves inside the second derivative, this guy right here, I'm going to get 2 over e to the third, which is positive. And the function e to the negative, the function, when I plug it into the original function, I get negative 2.25. So that is the absolute. So, but because the second derivative is positive, the function is concave up, and this point e to the 3 halves comma negative 2.25 is the absolute min on this interval from 0 to infinity. And yay! And that is it. We had a lot of fun. This is a relatively short chapter. Most of it is really just common sense. As I always say, the more you understand just the common sense of math, the easier it's going to be and the less mathy it's going to feel. I don't know if that's a real word, less mathy. That's the word I'm using. Anyway, it's been a lot of fun, and we'll see you guys next time. Bye.